So in section 2, we're going to talk about radian measure. And before we talk about radian measure, I want to review what an angle is. So when we're looking at an angle, over here we have angle A. It's when two rays meet at a common point. So in our picture here, our angle would be, we could refer to it as angle A, angle 1, or angle BAC or CAB. Those are all names for this one angle. It's where rays AB and AC meet. But we're mainly going to be dealing with angles where they are graphed on a coordinate plane in this module. So in that case, they have different definitions. So the first definition is the initial side, and all of these definitions are related to when we graph an angle. So the initial side of an angle is the starting ray, and that starting ray, when we graph it in a coordinate plane, is going to be on the x-axis. So if I were to draw an angle using a coordinate plane, my starting ray would be on the x-axis. So right here would be my initial side, the starting ray. The terminal side would be the ending ray. And it can be anywhere else in our coordinate system. So for example, I could have my ray end over here, in which case the measure of our angle would be this distance from where my initial side to my terminal side. So from my starting ray to my ending ray. So this position is called the standard position of an angle. So when we talk about the standard position of an angle, it's when the vertex is located at the origin. So vertex is located at the origin, and the initial side is on the positive x-axis. And I didn't specify in the definition of initial side that it's on the positive x-axis, but when we talk about standard position of an angle being graphed, we are talking about the initial side being on the positive x-axis. So next we want to talk about a positive angle measure and a negative angle measure. And when we talk about a positive angle measure, we actually create it by rotating counterclockwise. So when we rotate counterclockwise around the origin, that's how we get a positive angle measure. So if I were to draw a coordinate plane and my angle, positive direction starting going counterclockwise would be our positive angle measure. Now, we can also have a negative angle measure, and negative angle measures happen when we rotate clockwise. And again, this is around the origin. So if I use the same picture with my same angle, its negative angle measure would actually be starting at my initial side and going clockwise. So it has a negative angle measure, but they end up being the same distance. They do represent the same angle measure. It's just one of them is positive and one of them is negative. So let's go ahead and graph some angles in standard position, and then we're also going to talk about what quadrant our angle is in. So looking at our first angle of 172 degrees, it's helpful if we label each of our axes. So anytime I start, I'm at 0 degrees, and at the positive y-axis, I'm at 90 degrees. At the negative x-axis, we are at 180 degrees, and negative y-axis is 270 degrees. Because these are right angles, so every time we end on an axis, we've gone 90 degrees. So using that information, we can get a good idea of where 172 degrees is. So again, my initial side is going to be on my positive x-axis. And 172 degrees is just a bit above 180. So I know my terminal side is going to be somewhat a little bit above 180. And because it is positive, we go in the counterclockwise position. So when we talk about which quadrant the angle lies in, we always look at the terminal side, where that terminal side ended. So if remember naming quadrants, the first quadrant is always positive x, positive y, and then we move counterclockwise in naming our quadrants. Which means our terminal side ended in quadrant 2 for 170 degrees. Our next example is an angle with negative 300 degrees. So if we start by labeling our 0, 90, 180, 270, and then if I start back, I actually end up at 360 back at my original positive x-axis. So this time, for my negative 300 degrees, I'm still going to start on the positive x-axis, but in order to go negative 300 degrees, we're going to start heading down. So 270 would actually be a negative 90, 180 is a negative 180, 90 degrees would be negative 270, and then I need to go a bit more to get to negative 300. So negative 300, it's going to be actually up in quadrant 1. Again, because we've gone a clockwise direction from our initial side. So using the same labeling for quadrants, labeling the quadrants doesn't change just because we're doing a negative angle measure. So our quadrant that the angle lies in is going to be quadrant 1. So now that we've reviewed angles and how they're measured, now we're going to start talking about radian measures. And radian measures are a bit different in how we measure angles. So when we talk about radian measure, we're actually talking more of about a distance than what you're typically used to with degrees. So when we talk about what a radian measure is, a radian measure determines how many radii are in the arc length of your angle. And radii is just the plural of radius. So when we talk about radian measure, we're talking about arc length and radius. So looking at our picture here, we have that theta, our angle measure, which is equal to our arc length r over our radius r, is going to end up being 1. But we're always looking at how many radii are going to fit into our arc length from our angle drawn in a circle. So in our picture, theta equals 1 radian because the arc it intercepts is the same length as the radius. But it's not always going to be that case. So if we look at our example here, we want to know what the measure of theta is in radians. So in this case, when we do theta, we put the arc length of 8.7 over 4. We want to know how many times 4 will go into 8.7. So when you divide 8.7 by 4, we're going to get 2.175. And this is going to be measured in radians. It's not going to be measured in degrees like before. So radian has its own type of measurement, and it just becomes from dividing arc length by radius. So we like to be able to convert between degrees and radians in a little bit easier way. So in order to convert from degrees to radians, we multiply our angle by pi over 180. And when we convert from radians to degrees, we multiply by 180 over pi. And you notice that pi is going to be part of our answer for converting because the way we get these conversions has to deal with the circumference of a circle. And I'm not going to prove it, but you can always look up the proof of how we get the conversion between degrees and radians and vice versa. So let's go ahead and look at some examples. So we're going to convert our angles from degrees to radians, and then we're going to sketch the angle in standard position. So if I'm starting with the degree 200, to convert it to radians, we're going to multiply by pi over 180. And anytime we convert from degrees to radians, we're going to leave pi in our answer. So we're basically going to look at, so we get 200 pi over 180, and then we just want to simplify 200 over 180. So 200 and 180, I can divide. First, I can get rid of the 0, so I'm basically simplifying 20 over 18, which I can divide by 2. So we're going to end up with 10 pi over 9. And when we're looking to sketch the angle in standard position, we're going to want to, because we haven't talked about how to graph radians yet, I'm going to look at the original degree measure to figure out where the terminal side is going to be. So my initial side is always on the positive x-axis. 200 degrees, again, is going to, because I know the negative x-axis is 180, it's going to be a little bit below that. So going counterclockwise, because it's a positive angle, this would be about 200 degrees. So next we want to convert negative 120 degrees. So we're still going to multiply by pi over 180. So we get negative 120 pi over 180, which when simplified becomes negative 2 pi over 3. So again, in order to sketch my angle in standard position, I'm going to put my initial side on the positive x-axis, going negative 120 degrees. It's going to fall somewhere in my third quadrant, since I know negative 180 is in the negative x-axis. It's going to be somewhere down in here, and because we're going clockwise for a negative 120 degrees. And then lastly, we're going to convert negative 17.25 degrees to radians by multiplying by pi over 180. Now, negative 17.25 pi over 180 is not going to be a nice conversion. So I'm going to leave it as a decimal when I do the conversion. So that's going to be about negative 0.301 in radians. So I can see negative 17.25 degrees is not very many radians. So graphing my angle in standard position, starting with my initial side, negative 17.25 degrees is not going to be a lot of degrees. So I'm barely going to be moving my angle down in the clockwise position. So now we're going to go in the opposite direction. We're going to convert our angles measured in radians to degrees. So to convert to radians, we multiply by 180 over pi. And this time we're actually going to divide by pi. So we do 1.63 times 180, and then we divide it by pi. We're going to get roughly 93.39 degrees. So now that my angle is measured in degrees, it's going to be a little bit easier to graph in standard position. So my initial side, no 90 degrees is the positive y-axis, so 93 is not going to be much further than that. And it's the counterclock direction because it's positive. When we convert 2 pi over 7 radians to degrees, multiply by 180 over pi. And because pi is part of my original angle measure, I know I'm going to be able to cancel it. So we're basically doing 2 times 180, then dividing by 7, and we're going to get about 51.43 degrees. And then sketching our angle in standard position with our initial side on the positive x-axis. And 51 degrees is not quite to the positive x-axis, positive y-axis, so I know it's going to be somewhere in this first quadrant, and again, counterclockwise because it's positive. And then lastly, we want to convert negative 32 radians to degrees. So multiply by 180 over pi. So we take negative 32, multiply it by 180, then divide by pi, and we're going to get negative 1,833.46 degrees. So this is a very large angle measure. So when we go to graph it, since I know 360 degrees is one either clockwise or counterclockwise rotation, and because we're going negative, we're going to want to go clockwise, I need to figure out how many rotations I'm going to make before I get my angle. So if I divide negative 1,833.46 by 360 to figure out how many rotations that is, I get a little over 5. It's about 5.1, which means I'm going to need to do 5 clockwise rotations around. So 1, 2, 3, 4, 5, and then I go just a little bit further. So my terminal side is still going to be in this fourth quadrant once I do all of my rotations and then figure out what's left. And 5 rotations is about 1,800 degrees. That leaves me with 33 more degrees, which is why I know it's still going to be in that bottom right quadrant in quadrant 4. So let's go ahead and now talk about radian measures being graphed. So in this chart, we have our commonly used angles that we use, and we use our multiples of 30 and 45. Those are our commonly used angles for this module. So it's going to be helpful, and we're going to talk about this more in the next section, to know what its radian measure is. So if we start at 0 degrees / 360, so 0 degrees is 0 radians. And 360 degrees is going to be 2 pi radians. And I'm not going to continue writing radians for all of these, but they all have our radian after that. Then we move on to 30 degrees, which if I multiply by pi over 180, it's going to give us 1/6, so pi over 6. 45 degrees when multiplied by pi over 180 is going to be pi over 4. 60 degrees when multiplied by pi over 180 is going to be pi over 3. 90 times pi over 180 is pi over 2. And then we're going to continue multiplying and continue this trend. So 120 is going to be 2 pi over 3. 135 is going to be 3 pi over 4. 150 degrees is going to be 5 pi over 6. 180 degrees is going to be pi. 210 degrees is going to be 7 pi over 6. 225 degrees is going to be 5 pi over 4. 240 degrees is going to be 4 pi over 3. 270 degrees is going to be 3 pi over 2. 300 degrees is going to be 5 pi over 3. 315 degrees is going to be 7 pi over 4. And then 330 degrees is going to be 11 pi over 6. And we're going to talk more about this again in section 3, but you might want to keep this chart handy because it's going to be very important for the rest of this school year in pre-calc. So there are a couple ways we can apply radian measure, and one of them is finding arc length. So an arc is a portion of the circumference of our circle. So if you have theta, the degree in radians, the length of that arc, which is going to be L, is found by taking the radius of your circle and multiplying it by theta, your angle measure in radians. So L equals r theta, where L is the arc length and r is the radius. So looking at our first example, we have that the second hand on a clock is 5 inches long. How far does the tip of the second hand travel in 45 seconds? And then how long does it travel in 3 minutes and 15 seconds? So if we think of a clock, circle, we've got 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we're going to keep one hand of our clock fixed here at 12. And then our second hand, 45 seconds, happens at 9. So here's our second hand. So we know how far it travels. So we're just going from 12 to 9. So we want to know the length of this arc. So it goes from 12 to 9. So we have L equals, the radius is 5. Now we just have to figure out what theta is in degrees. So if we look back at that picture, 9, if we were to draw the x and y axis here, 9 would fall at 180 degrees, but we didn't start at the origin. We started at 90 degrees. So we start at 12, we go 90 degrees to the origin, then we go another 180 degrees to 9. So that basically is 270 degrees, which, using the picture from at the top of the notes, we know that 270 degrees is 3 pi over 2 radians, which when multiplied together gives us 15 pi over 2 as the arc length, which we can write as a decimal. Since we are talking about distance, it doesn't really make sense to leave our distance in terms of pi. So when we multiply 15 by pi and then divide by 2, we end up with about 23.56. And then our units, because our radius is in inches, is going to be inches. We also want to know how long does it travel in 3 minutes and 15 seconds. So if we think in terms of rotations, 3 minutes is 3 rotations from 12 to 12, and 15 seconds falls at the 3. So our second hand would end up on the 3. So in order to figure out how long it travels in the 3 minutes and 15 seconds, we do have to account for the fact that we've gone 3 rotations. So our total theta, we've gone 3 rotations at 2 pi, and we have plus the distance from 12 to 3 for the 15 seconds, which is basically 90 degrees, which is pi over 2. 3 times 2 pi is going to give us 6 pi plus pi over 2, which as one fraction is going to give us 13 pi over 2. So finding our length, our radius is still 5, but theta is going to be 13 pi over 2. 5 times 13, so we get 65 pi over 2. And again, it doesn't make sense to leave our answer in terms of pi for understanding purposes, so that's roughly 102.1 inches. So the second hand travels a long way. So now we want to find the central angle measure in radians of an arc of length 11 centimeters on a circle with radius 4. So using our formula of L equals R theta, we know the arc length is, so we know L is 11 centimeters. We know the radius is 4 centimeters. So plugging what we know into our formula, we end up with L equals 4 theta. So in order to solve for theta, we divide by 4. So we get theta equals 11 over 4, or 2.75 radians. Our last example says, how many inches will a weight raise if it is being pulled by a pulley of radius 9.27 inches and the pulley rotates 71.83 degrees? So this still is arc length because pulleys rotate in circular, but so we know L is going to equal R theta, but we're given theta in degrees, and in order to use arc length, theta has to be in radians. So we first have to convert 71.83 degrees to radians. The way we convert to radians is to multiply by pi over 180. So we take 71.83, multiply it by pi, and then divide by 180. We're going to end up with 1.25 approximately for theta. So plugging this in to our formula, we get L equals 9.27 times 1.25 for theta. So our arc length, 9.27 times 1.25, is going to be 11.5875 inches. Another way we can use radian measure is in sector area. So a sector is pretty much a piece of the area of a circle. So you can think of it as like pie slices are pieces of the area of a complete pie. So sector area is very similar in that. So to find a sector with theta in radians and a radius r, you do 1/2 theta r squared. So A is the area, and theta is our measure of our angle in radians, and r is our radius. So we want to find the area of a sector with a central angle of pi over 6 and a radius of 2.4 centimeters. So we can go ahead and plug that into our formula. A is going to equal 1/2, theta is pi over 6, and times 2.4 squared. So 2.4 squared is 5.76. So we're going to have 5.76 pi all over 12. So we could leave this as our area in centimeters squared. Our exact answer would be 5.76 pi over 12. But if we want to go ahead and figure out what that exact length would be, we multiply 5.76 by pi, then we divide by 12, and our area, we can also think of it as about 1.51 centimeters squared. And because this is area, our units are squared.